Hello. In this video, I'm going to discuss Green's theorem, which provides a connection between double integrals and line integrals of differential forms. Green's theorem was discovered by George Green, who was a self-taught mathematician in the early 1800s. He was actually primarily a miller who worked near Nottingham and taught himself mathematics through a subscription library at the time, and published an essay which contained Green's theorem, as well as several other advances in fluid mechanics and electromagnetics in 1828. And because of this, he was actually given entrance to Cambridge University as an undergraduate at the age of 40, and later became a fellow at Cambridge University. So he was a self-taught mathematician who discovered many very deep insights in mathematics, including Green's theorem, which I'm going to be discussing today. So Green's theorem gives a relationship between line integrals around closed loops and double integrals. And so if L is a closed loop, and so by closed I mean it starts at a given point and then comes back to that same point, then the line integral of this differential form, p dx plus q dy, around that closed loop is equal to the double integral of qx minus py over the region enclosed by the loop, which is labeled as r here. These subscripts are the partial derivatives, the partial derivative of q with respect to x and partial derivative of p with respect to y. So this works for any closed loop. In fact, L can be any curve that comes back around to itself, but we're just going to consider rectangles and disks because that's what we've considered, well, those are the sets we've considered doing double integrals over. This symbol for this line integral on the left-hand side of the equation just indicates that the integral is over a closed loop. So it begins and starts at the same point. Okay, this formula is Green's theorem. And to give a picture of what's going on, we'll consider this slide. So if we have a given loop L which goes around region R, and we should add that it goes around in the anti-clockwise direction as well. If it goes around in the clockwise direction, then the line integral is negative, and there would be a negative sign in one of these. So it's the closed loop that goes around in the anti-clockwise direction, as indicated here on the left with this ellipse, and on the right in this rectangle. Then we have this formula relating the line integral around the boundary of the set R, a closed loop around the boundary, to the double integral over the set R. And so let me do an example illustrating Green's theorem, and then I'll discuss a little bit more about why Green's theorem is true. So we want to apply Green's theorem to a line integral around the boundary of a rectangle, around a loop enclosing a rectangle, which is given on this slide. So let me first draw the rectangle. So here we have the x and y axes. And x goes from 1 to 2 in the rectangle, and y goes from 1 to 3. So this is the rectangle and the question. And the curve, the loop L, is the curve that goes around the boundary of this rectangle in the anti-clockwise direction. And the region R is the region enclosed by that rectangle, region inside the rectangle. And so what Green's theorem says is shown here. We should have that integral around this loop L, the curve that encloses this rectangle, of p dx plus q dy is equal to the double integral over the interior of the rectangle of qx minus by. And this is what it says in general. Now let's apply it to the particular example. So in this particular case, we want to consider the line integral around this boundary of this rectangle. of x dy minus y dx. So in order to make it match up with the notation here, let me write the dx term first. So minus y dx plus x dy. And so the p is minus y and q is x in this example. And so the right-hand side will say that this line integral is equal to a double integral of qx minus py. So we need to calculate these partial derivatives. This is the partial derivative of q with respect to x. So qx equals 1. And the partial derivative of y with respect to, the partial derivative of p with respect to y. py equals negative 1. Okay, so when we plug those in, we get that this line integral is equal to the double integral over this rectangle of qx is 1 and minus py, which is minus negative 1. So that's going to be a double integral over r of 2 dA. So this is a double integral of a constant, and as in some of the examples we've done in the past, we have a double integral of a constant, we just get that constant times the area of the region R. Okay, I'm sorry for the edit there, but there was a bit of a problem with the video. We have here this double integral is 2 times the area of R. So the area of R in this case is 2, as width 1 and height 1, and so 2 times 2 is 4. Green's theorem tells us that this line integral around the boundary of the region R is going to be given by 4, found it by doing a double integral. Now we can also compute this line integral individually, directly, just by computing the line integrals over each of the 4 curves bounding the region R. So I've added these in. So we're going to divide the loop L up into 4 sections, C1 on the right, C2 on the top, C3 on the left, C4 on the bottom, and compute the line integrals over each of those separately, add them up, and that gives us the line integral over the entire loop, which should be equal to 4 according to Green's theorem. So we're going to do that separately and check that in fact Green's theorem is correct in this case. All right, and so we want to compute this integral over this loop L all the way around the boundary of the rectangle of x dy minus y dx. And we'll do it by computing the integral over each of the segments making up the boundary. So the integral over C1 of the same differential form, which I won't write out again, plus the integral over C2, plus the integral over C3, plus the integral over C4. All right, so we'll do them all separately and check that they all add up to 4, as they should. And so first let's consider C1. So on C1, well, C1 goes from here up to here, and we can parameterize using the y variable. So you can't parameterize this using x, so let's parameterize using y. And we have that on this segment, x equals 2. And so dx is equal to 0. Right? Dx would be dx dy times dy, but dx dy is 0. And y goes from 1 to 3 in this segment. So y goes from 1 to 3. And so we can then calculate the integral over this first segment, C1. So the line integral over C1 of x dy minus y dx is equal to the integral from 1 to 3, because y goes from 1 to 3, of, well, dx is equal to 0, and we just have x equal 2, so of 2 dy. And so this is 2 times the length of the interval from 1 to 3, so 4. And so the integral over C1, the right-hand side, is 4. Now we have to do C2, C3, and C4. So on C2, the top, we parameterize using x, and so x goes from 2 to 1. So on C2, we use a parameter x, and we have that y is equal to 3 on the top, which means dy equals 0, dy dx times dx, 0, and x is in the interval from 1 to 2, and here it becomes important the direction of the curve. So in this parameterization, x is in this interval from 1 to 2, but in fact x goes from 2 on the right hand side to 1. So it goes from the right to the left. So the integral, when we set this up as a single integral, the limits have to be from 2 to 1. So the bottom limit is 2, the top limit is 1. So the integral over C2 of x dy minus y dx is the integral from 2 to 1, because x goes from 2 to 1 on this curve, considering the orientation from right to left, of, well, dy is 0, and y is equal to 3, and so minus 3 dx. And so because the bottom limit is bigger than the top limit, we get minus when we switch the limits around, integral from 1 to 2 of 3 dx, and that's just equal to 3. All right. So the integral over C2, the line integral over C2 is 3. Now let's do C3. And C3, we once again use y as a parameter. We can't write it as we can't use x as a parameter. And so C3 goes from y equal 3 to y equal 1. And on this C3, we just have x is equal to 1. X is a constant. And x equal 1. Dx, as before, when we did C1 equals 0. And y is in the interval from 1 to 3. And y goes from 3 to 1. This is, again, a case where the orientation of the curve is important. So the integral over C3 of x dy minus y dx is the integral. Y goes from 3 to 1. Dx is 0, and x is 1, so it's just dy. And so that's going to be negative the integral from 1 to 3 dy, and that's integral is just 2, the width of that interval. So negative 2. All right, we have one more segment left, C4, and then we can add them all up and check that we get the same result that we expect from Green's theorem. And so let's finally consider the integral over C4. So in C4, we use x as a parameter. Quickly go back up and look at the picture. So here's C4. X goes from 1 to 2, considering the orientation of the curve from the left to the right. And y is equal to 1 on C4. So we have y equals 1, dy equals 0, and x goes from 1 to 2. X is in the interval from 1 to 2, and when we parameterize it with the correct orientation, it goes from 1 to 2. So the integral over C4 of this differential form equal to integral from 1 to 2, x goes from 1 to 2, dy is 0 and y is equal to 1, so minus 1 dx, and so that is minus 1. Right, so we have the four integrals now. The integral over c1 is 4, c2 3, c3 negative 2, c4 negative 1, and let's add them up to get the entire integral around the boundary. So the integral around this loop L, which is the boundary of the rectangle of x dy minus y dx, is equal to 4 plus 3 minus 2 minus 1. So this was c1, c2, c3, c4, and that gives us 4. So this gives us the same result as from Green's theorem, and so George Green was correct, and we're successful. Okay, so this is an example using Green's theorem. Now I'd like to discuss a bit more why Green's theorem is true. I think that it's a surprising thing when you first see it, and maybe you'd like to understand why it's true. In fact, Green's theorem follows from the fundamental theorem of calculus once you've set everything up correctly. And I'm going to discuss the proof of Green's theorem in the case when R is a rectangle, which was the case we were just looking at. In fact, Green's theorem holds for other shapes besides rectangles, but in order to simplify this and give you an idea of why Green's theorem is true, we'll just look at the case of the rectangle. Okay, so here we have a rectangle, R, and it has four corners as shown. In this rectangle, x goes from A to B and y goes from C to D. And the boundary of the rectangle is a curve L, the loop L that goes around the boundary, and we've split up L into the four segments I'm calling here L1, L2, L3, and L4. And what Green's theorem says is shown at the bottom of the slide. The integral around the loop that's the boundary of the rectangle is equal to the double integral over the rectangle of qx minus py. So why is this true? Well, let's consider first the first term on the right-hand side, so the first term in the double integral over r of qx. And so if we were to write this double integral over r of qx as an iterated integral, integrating with respect to x first, it would give us this. And now the inside integral with respect to x, we can apply the fundamental theorem of calculus directly because we're integrating derivative with respect to x over an integral from a to b. So the fundamental theorem of calculus tells us that in fact this is just the integral from c to d of q evaluated at b minus q evaluated at x equal a dy. And then if we translate this previous line into line integrals, we get that in fact this double integral over r of qx dA is the line integral over L1 of p dx plus q dy plus the line integral over L3 of p dx plus qy. And so here we've used the fact that on L1 we have that y is equal to a constant, x is equal to constant b, and so dx is equal to 0. This is similar to what happened in the example we looked at. And so these two terms, or this term that is p dx is actually just 0 in this line integral. And then the q dy gives us this integral from c to d of q evaluated at x equal b. And similarly for the integral over L3. The negative sign here comes from the fact that L3 is oriented with with y going from d to c. And so we work out what these line integrals are. In fact, they give the previous line. And so this is the first term in the double integral in Green's theorem, in this case when it's a rectangle. The region is a rectangle. Now, what about the second term? We can do the same thing. So we have negative the double integral over the region R of the derivative of p with respect to y. As in the other case, we can apply the fundamental theorem of calculus to the inner integral here, the integral with respect to y, and get that this is a p evaluated at y, taking the two endpoints d and c. And then we can convert this to line integrals, as in the other case, the first term, and get that this is the line integral over L2 plus the line integral over L4 of p dx plus q dy. So then, note that in the third line here, converting into line integrals, we've used the fact that on L2 and L4, dy equals 0, because y is a constant on each of those two lines, similar to the example that we did before this. So we've figured out what the two terms in the double integral are. We've simplified them. And so we can combine this together, and we get that the double integral of qx gives us the line integrals over L1 and L3, and then the double integral of PR minus the double integral of PY gives us the line integrals over L4 and L2. And you add all those together, you get the entire line integral over L, is the curve that goes all the way around the boundary of this rectangle. So this is a proof of Green's theorem in the case when R is a rectangle. Of course, Green's theorem does hold for other regions, and the proof essentially follows from the fundamental theorem of calculus, similar to what I've shown, but it's more complicated when the boundary of the region is a curve. So this is Green's theorem for a rectangle. So in the final video in this section, I'm going to go over a few consequences of Green's theorem, so really applications of Green's theorem, and some more examples of applying Green's theorem.